Okay, we can proceed with the next, with the second talk of the day. Now we have Sanjiv, who is going to give a talk. The title is Substitution for Linear-Cartesian and Full Substructural Theories. Sanjiv, you can take the stage.
Okay, good afternoon, everybody, and thank you to the organizers for this opportunity to share some of my PhD research. This work is joint with my supervisor, Marcello Fiori, and yes, I'll be speaking about substitution for linear Cartesian and full substructural theories. So the perspective of algebraic theories as structures of substitution plays an essential role in understanding them as well, using category theory. For example, the composition in a Lawvere theory is given by simultaneous substitution. Now, one can take a different perspective, and rather than the substitution being captured by the composition of a category, the substitution can be captured by a structure internal to a category. This was done in 1999 by Fiori, Plotkin, and Turi for Lawvere theories, where they characterized them as monoids for a substitution monoidal tensor in a particular presheaf category. Similarly, in the 70s, although only published in 2005, Kelly characterized symmetric operads as monoids for a substitution monoidal tensor in a different presheaf category. And yeah, so this is the perspective we're going to be taking today. We'll start by going through the constructions of Fiori, Plotkin, and Turi, and Kelly in three ways. Firstly, concretely, in the way in which they originally appeared in the literature. We will then take a look at how the substitution monoidal structures can be induced universally. And then the third way is essentially the same as the second, but we phrase the universality in terms of symmetric monoidal theories. And this will allow us to consider other settings, such as affine and relevant theories, but moreover provides an appropriate general framework to generalize to the settings which we consider in the second part of this talk. We will consider theories which combine those mentioned previously. I'll go into detail on linear Cartesian theories, which combine the Lawvere theory and symmetric operad settings. Ultimately, my goal is to show you full substructural theories, which encompass all four substructural settings: linear, affine, relevant, and Cartesian. I'll exhibit some free-forgetful adjunctions between these theories, maybe the most interesting of which occurs between Lawvere theories, symmetric operads, and these linear Cartesian theories. And lastly, I'll make a few comments on other aspects of this work, both completed and in progress. I'll mention how these monoidal structures can be extended to bicategories in all of these settings. I'll mention how this approach can be used to study a much broader class of theories, and I'll make a brief comment on single variable substitution. Okay, so let's start with Fiori, Plotkin, and Turi's construction for Cartesian or algebraic or Lawvere theories. The easiest way to understand this construction is to take the syntactic viewpoint. So for some Cartesian theory, we can consider some term in context. If you'd like, the context is a scope of variables that can appear in the term. And importantly, in this case, the variables may or may not appear in the term and may appear multiple times. Looking closer at the context, we notice that the variables are anonymized in the sense of de Bruijn indices, so that the data of the context is rarely captured simply by a natural number n, how many variables appear in the context. This suggests that if one is to define a category of Cartesian context, which we denote by f, you take the objects to be the natural numbers. For the morphisms, you consider some other context, say with m variables, and you ask, how do I map the terms in the first context into the second? This is done by mapping the variables in the first context into the second, and then the term has its variables relabeled according to this mapping. So then the morphisms in our category F from n to m is a map from bracket n to bracket m, where the bracket notation around n denotes the set with n elements. This category is often referred to as the category of finite cardinals and functions, and it is equivalent to the category of finite sets. It has various nice characterizations, and two of them are particularly relevant to this talk. Firstly, it is the free co-Cartesian category on one object. And secondly, it is the free symmetric monoidal category on a commutative monoid. In both of these characterizations, the monoidal structure is given by natural addition, and the generating object is the singleton, 1. Okay. So now that we understand the context, let's model the syntaxes. And this is done by considering the category of covariant presheaves over F. I denote this by curly F, and I'll use this convention throughout this talk. So a presheaf P in this category can be thought of as some sort of Cartesian syntax, so that P at n is the set of terms for P in the context n. The morphism component of the presheaf is then just the term relabelings I mentioned in the first slide. And this is the setting in which we are going to model our substitution. And to do so, we again appeal to the syntactic perspective. So simultaneous substitution is given by taking a term t in some context with n variables and n terms ui, all in the same other context of m variables, and returning a term in the context of m variables, which is t, but with each of the variables xi replaced by the term ui. This suggests that if one is to define substitution on a presheaf P, it should look something like this. We want this natural in M, so we sum over all the different options for N, but this set is now too large. We take a quotient to identify the elements that are the same according to term relabelings induced by the base category. One quickly recognizes this coproduct quotient construction to be a coend, and so our operation for substitution looks like this. But to properly model substitution, one needs another ingredient. They need that P has a notion of variables. After all, substitution is performed by replacing variables by terms. This is done by defining the presheaf of variables, written V, and it's defined to be yoneda of 1. It's equivalent to embedding our base category into the category of sets. And the terms at each context are just variables. So to say that P has variables is simply to include a morphism from V into P as part of our data. So to phrase this all nicely, they introduced this substitution monoidal tensor, which is given for some presheaf P and Q by this Cohen formula over here. A bit of Cohen calculus yields that V is the monoidal unit of this tensor, and we indeed have a closed monoidal category, F circle V. Then the structure of substitution, given this notation on some presheaf P, is given by a morphism mu playing the role of the substitution and a morphism eta playing the role of the variables. But of course, this is just the data for a monoid with respect to this monoidal structure, and indeed, the axioms for a monoid directly correspond to the axioms which characterize simultaneous substitution. The unit laws tell us that substituting a term into a variable returns the term, and substituting variables into a term does nothing. The associativity law is simply the substitution lemma. We can then conclude with Fiori-Plotkin and Venturi's theorem that the category of monoids in F is equivalent to the category of Lawvere theories. Naturally so, Kelly's construction for symmetric operads is very similar. This now pertains to linear theories, where the terms are required to contain exactly one of each variable in the context. What this means for the category of a linear context, denoted B, is that the objects are again natural numbers, but now for morphisms, we take the bijections between the corresponding sets. You could call this the groupoid of finite cardinals and bijections, and it has the nice characterization that it is the free symmetric monoidal category on one object. To model the syntax, we then just take the category of covariant presheaves, and I note in passing that this is Joyal's category of combinatorial species. We can now jump straight into defining the substitution monoidal tensor, and this is given pretty much in the same way as before, with one so-called difference. Rather than taking the n-ary product of Q with itself, we take the n-ary day convolution of Q with itself. The day convolution is a monoidal tensor on a presheaf category, whose base category is already monoidal, and it's induced as the unit extension of the base tensor. anyway, we don't need to go into details for that today. The important aspect is why I said this is a so-called difference. And the reason is because the Day convolution inherits the structural properties of the base tensor. So for instance, in this case, because the base tensor is symmetric, the Day convolution on the presheaf category is also, and in the previous Cartesian case, because the base tensor is co-Cartesian, the Day convolution on the presheaf category is Cartesian monoidal. That is, it coincides with the categorical product. And so the previous construction was actually using the Day convolution underneath the hood. So back to our structure for substitution, we define the presheaf of variables v in the same way as your net of 1. And indeed, we have a closed monoidal category B circle V. And then the monoids for this structure model simultaneous substitution for linear theories. And we have Kelly's theorem that the monoids in curly B are precisely symmetric operads. Okay, so now that we have a concrete perspective on these constructions, we can view them a little bit more abstractly. And I should mention that the next part is already well understood by the literature and appears, for example, in Fiore's 2005 Fossacks talk. So firstly, for the Cartesian setting, recall that F is the free co-Cartesian category on one object, which makes F up the free Cartesian category on one object. This one object is a singleton, and we can specify it with a functor from the terminal category. Now, curly F, the presheaf category, is also Cartesian monoidal, either as a presheaf category or because the Day convolution is so. So specifying a presheaf there activates the universal property of F up and induces a Cartesian functor, making this triangle commute. And this functor is precisely the n-ary product of Q with itself from the previous construction. So we then take the Yoneda embedding of F up into curly F and take the left Kahn extension of this induced functor along it. Writing out this Kahn extension using its formula as a coend, we observe that this is indeed taking the tensor, the substitution tensor, with Q. This construction is factorial in Q, so we have our tensor. Of course, one still needs to show it's monoidal, but this is very easy. The unit is simply the composition of the top two functors, and the coherence follows from the universal property of the Kahn extension. The linear setting is just as easy. B is the free symmetric monoidal category on one object, and it is self-dual. So B op is also. And then the presheaf category, curly B, is symmetric monoidal with the Day tensor. And so specifying a presheaf induces this n-ary Day convolution of Q with itself. I'll refer to this as the tensor exponential from now on. We then take the left Kahn extension over Yoneda to get the substitution monoidal tensor, and the rest of construction follows as before. Okay, so the next part, we're going to be sort of changing perspective, and like the category theory behind it really is very similar, but the shift in perspective is going to turn out to be very useful. And the key observation now is that these categories of context are theories for symmetric monoidal equational presentations. So let me tell you what these are. Just like any other equational presentation, it consists of a signature, which has a set of sorts, set of operations, an arity function, which specify the sorts of the inputs and the output. Together with the signature, we have a set of equations, which are pairs of free terms generated by the signature in the language of symmetric monoidal categories. As an aside, this could all be done in terms of symmetric monoidal sketches in the sense of Hyland and Power, or could just be done in terms of Maclean's props. But equational presentations are nice and concrete and easy to manipulate, and so we go with this. Right, so for any presentation X, we have that it has models in a symmetric monoidal category C, and it also admits a theory, which is a free symmetric monoidal category containing a model of the presentation. This is equipped with the universal property that the models for the presentation are precisely the symmetric monoidal functors from the theory. We have the dual of all of this, that is that co-models are models in the opposite category, and the co-theories have the universal property that the co-models are symmetric monoidal functors from the co-theory. Putting this all together, we just have that the co-theories are precisely the opposite of the theories. Okay, let's now see this in action. For the Cartesian setting, the equational presentation is given by a sort C together with operations and equations for a commutative monoid. Then the models are simply commutative monoids, and the theory is our category F. The key point now is that the presheaf category, curly F, because it's Cartesian, we have that every object is canonically equipped with the structure of a commutative comonoid. The co-multiplication is given by the diagonal, and the co-unit given by the universal morphism to the terminal object. We then have the following. For each presheaf Q, we can induce the canonical commutative comonoid structure, and then we can use the universal property of the co-theory to induce this n-ary product of Q with itself. We then take the Left-Kahn extension over Yoneda to get the substitution monoidal tensor, and can consider the monoids to model the substitution and the theory. In the linear setting, the equational presentation is simply given by a sort L with no operations and no equations. The models are simply objects, and the theory is our category B. In the presheaf category, every object is certainly canonically an object, and so we can do the same thing as before to induce this tensor exponential for any presheaf Q. We then take the Left-Kahn extension over Yoneda to get the substitution monoidal tensor and consider the monoids, which characterize linear theories. What's nice about this is that we can extend it to the other settings, such as affine theories and relevant theories. Affine theories are those for which the terms may have at most one of each variable appearing in the context. The equational presentation is given by a sort A and an operation specifying a point so that the models are pointed objects, and the theory, denoted I on the right, is the category of finite cardinals and injections. The key point here is that the presheaf category is semi-Cartesian with the Day convolution, so that every object is canonically equipped with a co-pointed structure. Therefore, we can apply the same formula and induce this tensor exponential for every presheaf Q. We take the Left-Kahn extension over Yoneda to get the substitution monoidal tensor, and the monoids characterize affine theories. A relevant theory is one for which the terms are required to have at least one of each variable in the context. And so the equational presentation is given by a sort R with an operation and equations for a commutative semigroup. The models are commutative semigroups, and the theory is the category of finite cardinals and surjections. Here, in the presheaf category, the Day convolution is relevant monoidal, so it has diagonals. And so every object is canonically equipped with the structure of a commutative co-semigroup. Again, we apply this formula, and we get for every presheaf Q the tensor exponential. We take the Left-Kahn extension, consider the monoids, and we repeat the whole process. So the reason we want to phrase this in terms of equational presentations is that it allows us to consider more complex theories. And the one we're going to be going into detail on is Linear-Cartesian theories. So these are the ones whose contexts can have two different sorts of variables. Some of them can be linear and some of them can be Cartesian. Additionally, we have a coercion, which says we can turn a linear variable into a Cartesian variable, but not the other way around. If you want, you can think of this as some sort of dereliction. And these structures appear, for instance, in Barber's 1996 work on dual intuitionistic linear logic, and their substitutions have been studied as recently as in 2020 by Hyland and Tasson. Okay, so what is the equational presentation? It is given by two sorts, L and C, together with operations and equations on C, saying it's a commutative monoid. And then we also have an operation going from L into C, playing the role of the coercion. The models are then, as one would expect, they are morphisms such that the codomain is a commutative monoid, and so can be captured by this comma category over here, where U is the forgetful functor from commutative monoids. The theory, which we denote by L, takes a little bit more to describe than in the previous cases. The objects are quite simple. We're generating a symmetric monoidal category over two objects, and so we can take the objects of the theory to be a pair of natural numbers, L and C. And this represents a number of linear and Cartesian variables in a particular context. For the morphisms, if you'll excuse the pattern matching, we can describe any morphism from L sub L plus L sub C, comma C into L prime, comma C prime by two maps. Firstly, a bijection from L sub L into L prime, and secondly, by a function from L sub C plus C into C prime. The reason for this is that we may first always coerce some linear variables into Cartesian variables, and then map the linear and the Cartesian components independently. Now, this diagram over here describes a reflective factorization system, the corresponding adjunction for which I will now spell out. We can embed f into L by mapping a natural number n to the pair 0, n, and this embedding admits a reflection, which is given simply by summing the two components, L and C. We witness this adjunction by observing that for a morphism of the form on the right, we have to coerce all the linear variables because the ones that remain need to be in bijection with 0. But this is precisely to give a function from L plus C into N, which is what the morphism on the right is. I should mention now briefly that although we can include B into L also, this inclusion does not have a reflection, and there's some interesting technical reasons for why this is, but I won't go into details on that today. Now, this reflection induces an idempotent monad on our theory, which we denote by S, and the next step is to transport all of the structure into the pre-sheaf categories. So first we op everything, and so our reflection becomes a co-reflection, and our monad becomes a co-monad, and then we take the Yoneda restriction and extension of this adjunction to get this adjoint triple on our pre-sheaf categories. Note by a theorem of Im and Kelly that the left adjoints here are monoidal with respect to the day tensor. So then we also take the Yoneda extension of our comonad, and we get an idempotent comonad on our pre-sheaf category L, which we refer to as the Cartesian core. Explicitly, the Cartesian core of a pre-sheaf Q at a context LC is Q0C when L is 0 and empty otherwise. So the Cartesian core holds the terms of Q that only contain Cartesian variables. We're almost ready to apply that formula, but first we need to show that every pre-sheaf in L is canonically equipped with the structure of a co-model of our equational presentation, and this is where the Cartesian core comes in. For some pre-sheaf Q, in L, we can send it into F via the middle functor in our joint triple. And here it acquires the structure of a commutative comonoid because F is Cartesian monoidal. We send it back down along the left adjoint, and this commutative comonoid structure is preserved because the left adjoint is monoidal with respect to the day tensor. But this process is precisely what it means to perform the Cartesian core on Q. And so we get that the Cartesian core is always a commutative comonoid. But more than this, it's a comonad, and so it is equipped with a co-unit. This co-unit, with its domain being a commutative comonoid, is precisely a co-model of our equational presentation. We therefore can apply the same formula. For every pre-sheaf Q, we induce this co-model and then use the universal property of the co-theory to induce this tensor exponential. We take the left-Kahn extension over Yoneda to get the substitution monoidal tensor, by the way, the unit of which is Yoneda of 1, 0. And then we consider the monoids, which characterize simultaneous substitution for these linear Cartesian theories. We show these monoids equivalent to the appropriate notion, which one might call a linear Cartesian operad. We now move on to full substructural theories. These are the theories which involve variables that can be linear, affine, relevant, or Cartesian. And the story ends up being very similar to the one we just did, just with an extra few variables running around. So we'll take a bird's eye view of this construction. First, the equational presentation. While it may seem intimidating at first, all I've done is glue together the previous cases with coercions. And it comes equipped with equations which assert that C is a commutative monoid, A is pointed, R is a commutative semigroup, and that the coercions commute and preserve the operations that exist. Moving to the theory, which we denote by M, we have these various reflective subcategories of M. Note that A represents the theory for the combined affine Cartesian setting, and R the theory for the combined relevant Cartesian setting. Shifting to the pre-sheaf categories, we have that the adjunctions involving M induce idempotent comonads on the pre-sheaf category, the affine core, the Cartesian core, and the relevant core, while the other two adjunctions induce transformations between these comonads. These transformations, together with the co-units, allow us to construct a co-model of our equational presentation on any pre-sheaf Q. We then can apply the same formula, induce our tensor exponential, take the left Kahn extension to get the substitution tensor, and then consider the monoids, which characterize full substructural theories. I now want to exhibit some free-forgetful adjunctions between the theories that I've mentioned. But the point here is that this entire section can be captured by one simple statement, and that's that every inclusion of an equational presentation induces a free-forgetful adjunction. And I will illustrate this by looking at the Cartesian, linear, and linear-Cartesian settings. So at the level of the equational presentations, we of course have inclusions of the linear presentation and the Cartesian presentation into the linear-Cartesian presentation. But more than that, we also have an inclusion of the linear presentation into the Cartesian one by simply mapping the unique sort to the unique sort. Moving to the theories, these inclusions of presentations induce inclusions of theories by the universal property. And then I just want to mention that although the although the inclusion of F into L admits a reflection, the others don't. And this is not actually a problem here because this is not the adjunction we're after. The adjunction we want appears when we move into the pre-sheaf category. So this is given by the Yoneda extensions and the Yoneda restrictions. The theorem of Im and Kelly tells us the left adjoints here are monoidal with respect to the Day convolution. But the remarkable fact is that they are also monoidal with respect to the substitution monoidal tensor. That means that the right adjoints are lax monoidal, and this is important because lax monoidal functors preserve monoids. That means we can lift these adjunctions to the categories of monoids, but these categories are precisely those of linear Cartesian operads, symmetric operads, and Lawvere theories. Calculating what these adjunctions actually are, we see that they indeed are the free-forgetful adjunctions that one would want. And I would like to emphasize that this is completely general. It works for any inclusion of these equational presentations that we've considered today. So in the last couple minutes, I want to go over some other aspects of the work that I don't have time to go into detail on. And the first point I'd like to make is that if you're already familiar with this literature, you might know that the contemporary way of viewing these structures of substitution is not as a monoidal tensor, but rather as composition of one cells in a bicategory. To be a little bit more specific, in 2008, Fiore, Gambino, Hyland, and Winskill extended the substitution monoidal tensor in the linear setting to a bicategory denoted ESP. Now, this bicategory has objects as small categories and morphisms as a particular type of profunctor, in such a way that when you consider the monoidal Hom category ESP11, where one's the terminal category, you recover the pre-sheaf category with the substitution monoidal tensor in the linear setting. And then in 2018, they developed the theory of relative pseudomonads to do this in the Cartesian and the affine settings also. The point I want to make here is that we have done this generally for all the theories we have considered today. And in fact, this is maybe the easier way of looking at things, because the fact that the monoidal tensor, the substitution tensor is monoidal, can be deduced from the fact that the bicategory is in fact a bicategory, and all the monoidal adjunctions that I showed you just now derived from pseudo adjunctions between these bicategories. The next point I want to make is that you may notice that there's something a lot more general going on here, and it would be very reasonable to ask, does this work for an arbitrary symmetric monoidal equational presentation? And the answer is no, it doesn't. And we are in the process of investigating for which ones it does work. What we currently understand is that the sorts and coercions need to form a join semilattice, and that each sort needs to be equipped with arity-only operations that are preserved by the coercions. A simple example of this generalization happens when you take this joint semilattice to be, for instance, the total order on the natural numbers. What pops out then is what you could call a graded operad, which is like a usual operad, except where the leaves have levels or weights that now need to be preserved by the composition. As a last comment, I'd like to point out that all of these structures today pertain to simultaneous substitution, and while equivalent, they don't axiomatize single variable substitution. In that same 1999 paper, Fiori, Plotkin, and Turi provided a category theoretic model for single variable substitution and showed it equivalent to the monoids that we did discuss today. In a recent paper, Fiori and I have done the same in the linear, affine, and relevant settings. We would like to extend this to these combined situations, but for now, that remains work in progress. So yeah, it's with that that I will conclude this presentation, and thank you all for your time.
Thank you, Sanjiv. And now we move to question time. If someone has a question, they can raise their hand and ask it. So while people think, I actually have a question. Can you go to the previous slide? So here, if I look at the monoids picture, so the one on the top right, the right adjoints, are they fully faithful in this case?
So not always, not always. So some of them will actually be reflections, which will give this, but not in every case. So for the one that's less well behaved is the one that goes from B to F, and so for example, this won't have those sorts of nice properties. No.
But for example, the one going from LC op into law, this is fully faithful.
At the level of the pre-sheaves, at least, it is a reflection, and so should be preserved.
Okay, so then my question is actually, do you have a nice presentation of it as an orthogonality class in law, which is not just you take the reflection of the three guys?
That's a good point. So you want to induce some sort of factorization system there. No, we don't, but that's a good point. And
I would be curious to know if it is a nice orthogonality class with respect to some very nicely presented axiom in some sense. So in a non-tautological way.
Sure. I'm not sure that you'd be able to get something like that in law. In the more combined settings, you should be able to then make some sort of factorization going through the others. But yeah, uncertain on that, but we'll definitely look into it. Thanks. Yeah.
I'm not sure it's actually a good question. Maybe the answer can tell whether it's a good question. I don't know that.
That's true. That's true. Well, thank you at least for the question, Ivan.
Do we have other questions? Okay, if not, we thank Sanjiv one last time. Thank you, Sanjiv, for your talk. And